Hi everyone, my name is Mohsen and I'm going to talk about faster L2 validity proofs. This is a project that I did together with my colleague Pedro at our time at Zircuit. I'm now with Monad Foundation. So let's get into it and see how we went through this problem. The first thing that I need to establish before talking about the optimization is how does the optimism work when it comes to derivation. So as an L2, in order to be trustworthy for users, you have to submit all the transaction data on L1. So that's your anchor of trust. And once the data is submitted on L1, the rollup has this mechanism that continuously monitors the published data on L1, goes through all the blocks, validates all the transactions that are relevant for the DA, the call data and blobs, assembles back those frames and channels, these compressions that Optimism does, and then executes those recovered blocks from L1. So basically, the entire state of L2 is dependent on what is already shown on L1. And at this stage, the rollup is considered finalized or secure. And against this secure state, you can do your withdrawals. So basically, everything is anchored on L1. You have a role of a batcher here that submits your DA, the list of transactions compressed to an inbox, and that's the role. That's the actor actively involved in doing that. Now, if you want to do validity proofs for rollups, the typical way of doing that is to have a range proof, so a set of blocks. You can decide how large that set is going to be. So it could be 100 blocks. You do a state transition for each of those blocks. You check everything, and then you compute a range proof over that one. And you need to pass the list of transactions as input to a range proof. You don't want to submit the range proof directly to the chain because it's going to cost a lot for every range that you have to submit a proof. You rather want to use recursion in your scheme and compress and aggregate all those proofs of your ranges into one aggregate proof that you periodically submit on L1. So this continuity of those ranges is verified by the aggregate proof. And once that proof is available on L2 output Oracle, then you can basically start withdrawing. The chain is basically 100% finalized. Now, we did the migration to zkVM. We were using SP1, and we saw that contrary to our original benchmark that we did, the ranges were expected to be between 4 to 5 billion cycles. But we had some set of very mysterious ranges that they kept popping up rather consistently, and they costed 10 times more. So they were in the magnitudes of 40 to 50 billion cycles. And this was 10 times more than what we expected that we would need to prove those ranges. And this happened consistently. Then we started investigating. We looked through the breakdown of the proofs, and we were looking at which part of this range proof computation is taking most of the cycles. And turned out that derivation, the process that surprisingly I spoke about a little bit in the very beginning, that one is taking most of the cycles. So most of the effort is spent in that basically derivation step, 85%. The execution, just set of L2 blocks with L1 deposits, only considered 10% of the entire time spent in the proving. And everything else was just negligible, less than 5% for decompression, and everything else you were doing was just basically nothing. 85% is pretty much. Why is 85% of the time into derivation wasted? So for that, we had to look deeper and do some instrumentation and see which step exactly in derivation is costing that much. And I need to go very quickly over high-level idea of what those are. So derivation basically fetches all the blocks that are deemed relevant for deriving the state of L2, and that's basically L1 block filtering, fetching. Once the blocks are fetched, then all the receipts in those blocks need to be checked. because the protocol has some update path that you can change the batcher. So those events that are relevant for the derivation process need to be all processed as well. Then there is this filtering for TX for transactions that bear any DA data, so any call data or blobs. So that's basically going through the transactions and finding those DA-bearing transactions. And then frame assembly and everything else. And those are rather quick. So those two boxes that I have in red, those are the expensive operations in the derivation. So most of the cycles were spent exactly on those two. And then while you were looking at this, we had an idea of why this is very slow and how this is happening. We had an incident. So over the weekend, there was a batcher timeout. So the batcher stopped submitting the DA transactions for a course of 9 hours, we think. And then we ended up with some ranges that needed more than 100 billions of cycles to be proved. And that basically means we cannot do that. So we have to skip over those. So we have to skip those things in our testnet/devnet. So those are basically a denial of service threat, basically, that we are seeing here. This situation was much worse, actually, on testnet, on Sepolia. And we were puzzled, if this is a deterministic behavior, why on Sepolia we're seeing much worse results than mainnet? And in hindsight, it's actually quite simple. On Sepolia, at the time of the analysis, blocks were much more filled because you don't pay for those transactions that you're submitting on Sepolia. So I assume people are submitting more on the testnet. So we have, on average, 278 transactions on Sepolia, and mainnet is 192. So it's like 45% more transactions, and this directly correlated with the higher cost that we saw on Sepolia. Now let's take a closer look. I already spilled the beans. But let's take a closer look and just spill it out. The bottleneck in the pipeline is basically once you have L1 blocks that are deemed as relevant for the derivation, there is this step that scans all the transactions in those blocks. And this is a complexity of O of transactions in the block. It's linear, but those transactions could be quite a lot. And after the filtering, you will be ended up with a set of transactions that are relevant for the derivation. So those are batcher transactions. And that's a very small subset of all the transactions that are on L1. So here the inefficiency is that you have to traverse so much to just extract so little of transactions that are relevant. And to give you an example, 382 relevant blocks identified by the derivation process would have 73,000 transactions in them. And scanning all of that, you would only need something around 15 transactions out of all of that. So you can see how much wasted computation is done here to just find those 15 transactions. What we want, so I already explained the left side, so full traversal. You have the host, fetching all the L1 blocks and passing them to the zkVM to compute, and find the list of DA transactions for you and do the derivation. This is very high overhead expected here. What do you want to do? We want to actually do the host to do a little bit more work outside the zkVM. We want the host actually to do sparse or do a search of transactions outside the zkVM, find those 15 transactions that we deemed as relevant or how many they are, and then only pass those subset of transactions inside zkVM, right? Here's a little bit of problem though. If we just did that, just pick those transactions we deemed relevant and pass to zkVM, we could violate some safety guarantees. So we would have some soundness issues. Let's get into that. What could be potentially a problem if we filtered everything outside zkVM? So number one is basically soundness problem of allowing the host, the untrusted entity, to basically omit any DA, reorder the DA, or basically replay the DA, because the zkVM only sees the set of transactions that it is told to trust and derive from them. So basically, if the host is cheating, it can pass whatever transaction it wants, and then the zkVM would just accept them. So one quick way or one easy way to solve this problem would be actually introducing this nonce continuity. For the list of transactions that are passed inside the zkVM, we say, okay, all these transactions must have this incremental, continuously growing by one transactions. So if you skip any transaction, if you reorder, so the nonce would not match. And under the assumption that the batcher only submits DA-related transactions, then we are covering this problem of, introducing gaps or omitting or reordering. So this should be solved. There is one catch though here. The batcher itself could be modified, could be updated, and that would be a protocol level change. I'm not going to get into that, but this is something that we also consider and deal with it as well. Another problem is if you just look at the nonces and give list of transactions, still the host can actually do some attacks. They can forge. They can say, oh, this is the transaction, here is the nonce, go for it. So the signature needs to be valid. It must be from the batcher. They can also, make a transaction that has the signature, but is sent not to the batcher, but somewhere else, right? So you still have the nonce continuity. You have the signature matching, but it's sent to somewhere else. So tx.from needs to match the protocol level batcher. It has to be from the batcher that we care about, currently set in the protocol. tx.to should be the batcher, the batch inbox. And, if any update happens, we need to be able to detect it. And that's the next optimization that we introduced to solve this problem by looking at logs blooms. There are no false negatives in logs blooms. So we basically look for any update events rather than going through all the receipts. We look for any update events. If we find them, then we say, okay, this is the sender. The sender must be this address. And that problem would be solved as well. The third thing, now, so far I talked about the ranges. So each range needs to have this continuity of nonces. The data has to be authentic. It must be sent to from the batcher, and it has to be sent to the inbox. But so far we only have these guarantees at the level of the range. So each range has all these soundness properties that we care about, right? Now, there is no check cross boundaries because we do separate ranges for each set of blocks. We do one range proof, the next set another range proof. And now this one would have the nonce continuity and all the checks we want. The next one starts on its own and it would have its own nonce continuity. So in between, I can basically skip a nonce, right? And there is no way for these proofs to know about the skip nonce or change of sender. So we need to introduce another soundness check at the level of the aggregate proof, and that's basically by ensuring across the ranges the nonces are still consistent and the sender is still matching. So we are taking away one of the optimism features here because you can update the batcher on the fly to whatever batcher you want, but for the standard practice this is not a big limitation because if we introduce a new lane that you can update the batcher address as you wish, but those must go through a different lane, cannot go through day-to-day range and aggregate checks. You have to update that separately, and this check of the sender and nonces has to be intact for any normal operations that you are doing. Very small, overhead. If you are changing your batcher address, which we never did at the time we were operating, but if this is something you need, that's something that you have to address in your maintenance flow, and it doesn't have to be part of the critical path of your application. So now I have covered, the optimization itself, filter transactions, and then introduced these soundness checks, why we need them, what kind of attacks we are mitigating with those, and implementing the scheme itself. So after implementing this sparse filtering, we noticed 6.5x speed up in the derivation. So the derivation is significantly faster. Overall speed of the end-to-end proving for those ranges, 3.5x faster. So the ranges are being computed much, much faster now. And for different channel duration, the timeout that you're submitting your batches, these gains could be different. So now, opposite to what it was in the unoptimized version or the baseline, the longer you wait, the larger set of blocks that you have to actually consider in your derivation, the wins are actually much bigger. And this is useful because if you more frequently are submitting the DA, you have to pay for the gas of those DA. So you can find the sweet spot that you submit less, without sacrificing, the efficiency of your range proof. This is something that on the baseline you cannot do, because you can see at the baseline with 500 millisecond, we basically have almost 5 billion of cycles. And this is the unoptimized version. With the optimized version, this has dropped to 1.4 billion, basically. Okay, so what are the key takeaways? What we did look at here, and what did we learn from this? So first off, zkVM, amazing tech. You can just take a program written in Rust and just run it on the zkVM backend. And then you can have verifiable execution, which is amazing, right? This doesn't work well for all programs in a way that the performance is going to be maybe far lower than what you expect it to be. There could be some edge cases also that you might not see immediately. So in our case, our initial test showed really good results. We were very happy with that. But with some pile up of the DA, we saw that it was much worse. Denial of service attack, or a risk of denial of service, if this data piles up, then maybe you cannot even prove it anymore. Although the zkVM can do any Rust program, but if your program has this risk of having way too much input, if it piles up over time, unbounded input, this could be actually a denial of service risk. We designed a sparse input, so we optimized the data that goes into your zkVM, but I showed you that actually this is not enough. Just optimizing the data is not enough. We needed to introduce some soundness guarantees here as well. And this was done by tracking nonces, signature checking, and L1 anchoring, so having the nonce across the ranges for the aggregate proofs. With this kind of optimization, 3.5x faster proofs, we basically we get much closer to real-time proving. And if I want to say broader impact of this could be applied to any zkVM application that deals with large inputs partially relevant for the actual computation. The same technique could be applied. Verifiable execution doesn't necessarily mean efficient execution, and if it's efficient, doesn't necessarily mean it's going to be sound. The source code is fully open source. You can take a look at the code yourself. The preprint is also an archive. You can see my Telegram. You can reach out to me if you have any question. If you're working on similar problems, I would be more than happy to answer questions and give you some feedback on the design you're having. More than happy to help in any way. Thank you. If there are questions, well, thank you very much.